Welcome to One Chemistry. Always try to do your best. Now, let us see about 100 concepts in organic chemistry. We are seeing it as episode. This is the episode number 63. If you didn't watch previous episodes, I encourage you to go and see. Here, we solve 5 problems step by step. Stay tuned. Let us see the first question. You are having pyridine there, you are using nitration. They ask you to find the product. Whether products or nitration occur at the second position or third position or fourth position or dinitration occur or not is the question here. Basically you have to find position of nitration as well as dinitration possibility. So from the pyridine and possible 4 answers you might realize the question is really about regioselective NO2 addition. The answer is B. Let us see how. Basically you are conducting nitration. What nitration will do? At first step it will attract electron from the ring. There you have cation formation. Now let us look at the cation formation there. If the attack happened on the third position, you have the cation formation all over the ring without the cation on nitrogen. So no positive charge on nitrogen and all resonance structure. If you look at the second one, even the first step itself you have cation formation at nitrogen. Similarly happened with the third one, where the nitration happened at the third position, slowly it transferred to nitrogen there. Nitrogen is the electronegative atom. What really happened is it will withdraw the positive charge, it make it very unstable. So the cation on the nitrogen is very much unstable. So only we can have the possibility of B there. There is no cation on nitrogen there. Another important thing you should learn is dinitration is not possible because after the first nitration ring will become electron deficient, so reaction will not be possible. Here the concepts you have to learn here is positive charge on the electronegative atom is very much unstable. Once the ring become electron deficient, the electrophilic attack will not be happen there. Then let us look at the next question. The starting metal they are asking, they are using the base, formation of lactone is there. Lactone means a kind of cyclic system with ester. So you have to find which one can form the lactone easily. They given the 4 different structure. A1 is cyclohexane with alcohol and ester. They both are trans to each other. If you look at the B, OH and same COMe are cis to each other but on 1,3 position. If you look at the C, you have the same system with methylated one, but both methyl are trans to each other. If you look at the D, the configuration can be any, but you have to look at the possibility of lactone formation. Basically they given the 4 different structure with 4 different position of functional groups. So from the question of lactonation and possible 4 structures, you might realize the question is really about structure versus reactivity. The answer is A. Let us see how. For the lactone formation, ester and OH should be cis, favorable for 6-member ring formation. But our starting metal is trans there. Let us have the cyclohexane structure to understand better. You have to maintain the same relationship. OH and ester should be trans to each other. Here you have one acidic hydrogen which is near to COMe, so the hydrogen is acidic there. So what really happens is you can withdraw the proton that can enolize. While enolizing, it will lose the difference between axial and equatorial. What really happens is it can isomerize to axial there. Then if you use the base again, it will abstract the proton. You have the cyclic ring formation. So enolization create the double bond there, so it lose the difference between cis and trans. What really happens is COMe become axial there. So the axial can be attacked by OH easily, which can lose the proton there and attack it. OMe is a good leaving group, you have ketone formation. So it's a lactone formation there. So the cyclic ester, so it's called lactone. So the answer is clearly A, both are trans to each other, but during the reaction it becomes cis and reactive. Here the concepts you have to learn here is, whenever you use the base, you look for the acidic hydrogen. If it is there, you might think of enolization if present with carbonyl group means. Then let us look at the next question. They are asking mesoform of 2,3-butane diol. Butane attached with 2OH group in 2,3 position. So they given the Newman projection. They given the 4 different staggered form. First one is all are trans to each other, or you can say all are anti to each other. CH3 is anti, hydrogen is anti, and OH is anti. If you look at the B, the CH3 group are anti to each other, but OH group are kind of gauge conformation are nearby to each other. If you look at the C, the same thing, it's the mirror image of B there, it's a enantiomer. If you look at the D, it's a kind of partial antiposition. CH3 OH are anti to each other. So you have to find which one is meso there. So from the question of meso and the possible 4 different Newman projection, the question is really about structural conversion and symmetry elements inside. The answer is A. Let us see how. Here the meso form is in question. Meso means superimposed mirror image. The quick trick will be mirror plane inside. Here we have to draw in terms of Newman projection to Fisher projection. So we have to bring all eclipse form together. So CH3 is behind CH3, OH is behind OH, H behind H. For that you have to rotate 180 degree, bring CH3 together. It will be easy thing. Then you can convert it into Fisher form. What really happen is CH3 at terminal, HOH on the middle there. So if you look at it clearly, it's a mesoform. Mirror plane go with the middle of the system. So dotted line representation of mirror, it reflects both sides the same molecules. So the answer is clearly A there, it's a mesoform. Here the concepts you have to learn here is, you have to know how to convert Newman projection into Fisher projection. Same thing is, only the anti-groups leads to the mesoform, not gauge form. Then let us look at the next question. You are having conjugated ketone there, which is alpha, beta unsaturated ketone. You are using lithium, copper, methyl. You are using organomethyl, which is with lithium and copper. They ask you to find the product. The products are mostly the methylation occur at the first position, methylation occur at the fourth position, or methylation occurs with retention of double bond, or a kind of insertion on the double bond. So the 4 different possibilities. So from the question of alpha, beta unsaturated ketone and the soft nucleophile, you might realize the question is really about regioselective methylation, where the methyl group forms. The answer is A. Let us see how. Here the concepts you have to learn here is hard soft acid base theory or HSAB theory. The concept is soft nucleophile always attacks soft center, or you can say weak positive charge. Here I given the numbers there 1, 2, 3, 4. The reagent you are using is called Gilman reagent. It's a soft nucleophile producing reagent. It is a Me-1. Here Me- can attack 2 position or the 4th position. That decides the product there. If you look at it, carbon has positive charge and the double bond has positive charge. The double bond one is kind of weaker one because it's derived from the carbon there. So it will be weaker and it is soft. So soft nucleophile attack the soft center. So it will attack on the 4th position. So 4th position attacks, the double bond travels and O- is established there. Then if you protonate it, OH is formed. Then if you do hetoenol tautomerism, you have the desired product, which is 1,4 addition product. So the answer is clearly A there. Here the concepts you have to learn here is hard nucleophile will undergo 1,2 addition, which is derived from RMGX. Soft nucleophile, which derived from lithium copper, undergo 1,4 addition. Then let us look at the next question. The question is about the acid which can undergo fastest decarboxylation. The A1 is with carbonyl group attached with phenyl and acetone on either side. Then you have B1 which is phenyl and the CH2COH on other side. D1 is the chiral one, which is a kind of hydroxy group attached with either side phenyl and acid there. So they given the 4 different structures. So from the question of decarboxylation and 4 different carboxylic acid, you might realize the question is really about functional group versus decarboxylation. The answer is B. Let us see how. Here the decarboxylation occurs with the assistance of hydrogen bonding. So you have to know which structure can form hydrogen bonding easily. So if you take the B1, if you redraw nicely for our intermediate, it will have hydrogen bonding. What really happens is the OH and acid hydrogen bonded with nearby carbonyl group. So what really happens is 6-member transition state is formed. The stable 6-member hydrogen bonding thing, it will help the CO2 to leave. CO2 is the good leaving group, it will need little trigger to leave there. CO2 leaves, you have final product alcohol which is enol one. It will convert it into aldehyde or ketone there. So the answer is clearly B, which is carbonyl with CH2COOH. Here the concepts you have to learn here is you have to choose the carbonyl group which will be on alpha gamma position. Then it will form nicely 6-member transition state. That's all from this episode. I hope it was easy. Thanks for watching. If you have any suggestion, comment below. Stay tuned for next episode.